June 3, 1998. It is 10:58 a.m., and InterCity Express train 884 is moving north through Lower Saxony at nearly 200 kilometers an hour. Somewhere south of the German village of Eschede, a hidden fatigue crack on the third axle completes its journey. The steel tire splits. Centrifugal force holds it briefly before catching the rail. The tire unwinds into a 2.5-meter steel ribbon, punching directly up through the cabin floor. The resulting sequence of events triggers a derailment that shears the supports of a 300-ton road bridge, collapsing it directly onto the passing carriages. 101 people died, and 88 more were injured. This catastrophic multi-point failure of infrastructure was the direct downstream result of a single localized mechanical fracture. After breaching the cabin floor, the broken tire remained attached, dragging violently beneath the carriage as the train covered another 6 kilometers of track. Approaching the bridge, the train passed railway switch points. Switches are engineered to handle massive downward force from above, not strikes from below. The dragging steel ribbon wedged the switch upward, throwing the track alignment completely in the wrong direction. The front of the train cleared the switch, but the thrown points violently diverted the third coat onto a parallel track, driving it sideways directly into a slender concrete pier supporting a local road bridge. Bridges are built with redundant structural margins, but those margins account for gravity and standard loads, not a lateral kinetic strike from a train moving at cruise velocity. The supports sheared instantly. To understand why that specific wheel failed, we have to look back a decade. Deutsche Bahn was building the ICE network, Germany's response to the high-speed rail systems emerging in France and Japan. Early prototypes ran on standard solid steel monoblock wheels. But at high speeds, those solid wheels generated a low, pulsing vibration. It was a harsh ride, causing wine glasses to chatter in the dining car. To solve the noise problem, engineers adapted the BA064 wheel, a rubber-sprung design borrowed from the low-speed Hannover tram network. It featured an inner steel hub, a 20mm ring of rubber blocks, and an outer steel tire clamped around the assembly. On a city tram at 50 kilometers an hour, the rubber dampened vibrations. But scaling that design for a train moving 5 times that speed created a new problem. Centrifugal forces pull the outer steel ring outward, warping the rubber and flexing the tire. Prioritizing subjective ride comfort over verified high-speed dynamic testing created a structural vulnerability that was never fully quantified. This chart shows the relationship between tire thickness and structural stress. The high-speed wheels were manufactured with a starting diameter of 920 millimeters, and regulations set an absolute retirement limit of 854 millimeters. That gap seems like a wide safety margin, but as millions of rotations grind the outer steel tire thinner, cyclic stress concentrates heavily along the inner circumference. The physical stress on the metal does not increase linearly. It spikes sharply as the tire loses mass. The specific wheel that shattered on train 884 had worn down to 862 millimeters. It was 8 millimeters above the legal limit, remaining in active service while sitting on the extreme exponential end of the stress curve. Adherence to static, linear wear limits creates an illusion of safety when the underlying physical degradation is nonlinear. Even with a flawed design, rigorous maintenance routines exist to catch mechanical failure before it leaves the depot. Material fatigue in this design exclusively originates on the hidden inner circumference, where the steel tire meets the rubber blocks. To find these fractures, you need eddy-current testing. This non-destructive diagnostic tool uses electromagnetic fields to detect microscopic anomalies beneath the metal surface. The Munich depot had these machines, but early in the ICE program, they threw frequent false positives, causing train delays. Administrators prioritized schedule over diagnostics, quietly retiring the equipment. The replacement diagnostic protocol was manual inspection. A technician simply walked the length of the train with a flashlight, checking the outer rim. The inner fatigue fractures lived completely in shadow. The maintenance workflow was compromised because an objective sensing instrument was abandoned in favor of an inadequate visual check. Without the right tools, the depot was blind. But the train and the wider rail network were still generating massive amounts of data about the impending failure. In late 1997, Üstra, the operator of the Hannover trams, found identical fatigue cracks across their fleet. They issued a written warning to every operator using the rubber-sprung wheel design. Deutsche Bahn received the warning, filed it, and initiated no fleet inspection. In the 2 months before the crash, the onboard diagnostic computer for IC-884 logged 8 independent complaints from staff. Conductors and dining staff repeatedly reported localized humming and knocking from one specific bogie under Coach 1. In the final week, 3 separate automated trackside sensors physically flagged a wheel on that exact train as defective. 3 independent systems registered the fault. Every time, the train was cleared back into service. The disaster occurred because administration normalized the act of ignoring redundant warnings. This administrative inertia continued right up to the final seconds on the morning of June 3rd. When the steel tire punched up through the floor of Coach 1, a passenger immediately left her seat to find a conductor and report the massive piece of metal protruding into the cabin. The conductor listened, but rigid operational protocol required him to physically walk back to the carriage and visually confirm the damage before engaging the emergency brakes. While he walked the length of the train to investigate, the carriage covered the final 6 kilometers of track, carrying the broken steel ribbon directly into the points of the railway switch. A procedural rule intended to prevent unnecessary train delays became the final point of failure, overriding the immediate human emergency. In the aftermath, the Fraunhofer Institute's investigation was definitive. The rubber-sprung wheel design was incompatible with high-speed rail parameters. The specific wheel class was immediately withdrawn from high-speed service, and the use of objective eddy-current diagnostic testing was reinstated across the maintenance fleet. Even the physical infrastructure was redesigned. Road bridges over rail lines were rebuilt using cantilevered architecture, eliminating the central piers so a single track collision could not trigger a total structural collapse. A decade of localized decisions, prioritizing comfort over testing, replacing sensors with flashlights, and enforcing rigid protocol over human observation, converged at 250 kilometers an hour to create the disaster. The train's diagnostic network accurately measured the deteriorating conditions, generating 12 distinct warnings before the metal sheared. The tragedy of Eschede is that the data was there,